Hello, my name is Johan Tekel. Welcome back to our Internal Forces tutorial series. Today we're gonna go up to level 5 and complete that level. Since we've done this for 4 levels already, I've explained a lot of stuff already, a lot of tricks that we're using. So I'm not gonna be that explicit in the explanations anymore. I'm gonna try to keep it short. So with the single load we have here on the cantilever beam, the beam will bend downwards if we think about the deflection line, causing tensile stresses to be on the upper side of the beam of the cantilever. And what we say is that moment are on that tensile side. So basically upward negative value, and from the end of the cantilever to the single load, we couldn't have any moment there. Here, what's gonna happen when we look at the beam, our trick for the shear forces was to look at the beam from the right to the left, and we would have here a vertical force at the roller support going upward with half the value of the single load of the external load going upward. So we have a jump to the negative values, then the distribution stays constant because we have no distributed load, then it jump back in the positive value, stays constant again, jump back to 0 at the left support. Here's the answer. This element here is purely under compression, so we should have a negative normal force like this one. What happens here? This is pure bending. And if we think about how this cantilever will deform, it will cantilever end, the end of the cantilever will basically go upward. The tensile side would be the lower side of the element, so the moment would be a positive one. That's the little trick we had for that. We could also cut through the beam and perform a moment equilibrium, of course. So the single load we have here on the cantilever beam at the end of the cantilever beam is gonna cause a bending of the system downwards, leading to tensile stresses on the upper side of the cantilever beam. So the bending moment needs to be on the upper side, so a negative one. Now this right answer here is wrong because we have a quadratic function there. That's not possible without distributed load. This one here in the middle is 1 because at the right end we have a value already that's not possible without a single moment, so the left one is right. But looking at this simple supported beam, at the right roller support the value of the moment should be 0. At the left pin support that value should be 0 too. And with this loading going upward when it comes to the vertical components, we should have a bending such that the tensile stresses will be on the upper side of the beam. So the moment distribution will also be on that upper side, meaning negative values, and due to the single load we need to have a king, so the right answer here is correct. Good. Looking at the beam from the right to the left, we should have a linear distribution going upward. Linear distribution going upward from the right to the left. That's our trick. Yeah. Looking at this system too, from the right to the left, we need to have a jump downward first, so a jump to the positive values. Okay, all of them are doing that. From the right pin support up to the hinge, that's a rod. That rod can't have any shear forces except if it's loaded perpendicular to its axis, and that's not the case here, so we can't have any shear forces in there, so the middle answer here is wrong. And now the jump, the normal force in that was gonna bring us back to negative value. So here's the answer. Looking at this element from the right to the left, we should have a linear distribution going downward in the direction of the distributed load. That's a trick we've explained already. So this one is wrong because looking at this distribution, the right answer here is wrong. Looking at this distribution from the right to the left, we're going upward. That's wrong. This one is wrong because it's constant. So here's the correct one. Looking at the distribution, the shear force distribution from the right to the left will going downward, like the distribution force is also applied downward. Okay, moment equilibrium here at the pin support would lead to a vertical force at the roller support going upward. And due to that vertical force, we're basically gonna have a positive moment first. We don't have to forget the distributed load that would lead to a quadratic distribution. So this right answer here looks really good. Here the curvature of the quadratic distribution is wrong. And over here, there's no reason for that moment to change signs. So the right answer was correct as I said earlier. Moment equilibrium at the left pin support will lead to a vertical force at the right roller support, vertical force with the value of half the external load. And that vertical force will lead then to a positive moment when we think about how that vertical force wants to deform the system. Positive moment up to the frame corner, and then the value it just stays positive and go on the other side. So the answer here is the right one. Don't even need to look at what happens there on the other elements. So the right answer is 1 because a quadratic distribution, we don't have any distributed load. The middle answer is wrong because on the right at the roller support we don't have a single load. We can't have a jump there without single moment. Single moment I meant not single load, single moment. So the answer is this one. On the left pin support we have a value of 0. On the right pin roller support have a value of 0. We have a kink due to the vertical load in the positive area. So the left answer here is wrong because of the way the distribution of the shear forces is. It's going upward instead of downward, looking at the element from the right to the left. This one here is wrong because on the horizontal part, due to that single load, we need to have a jump downward in the positive area. I'm looking at the element from the right to the left. That's why this one is wrong. So here's our right answer. Good. Due to the parallel motion, the shear forces need to be 0 at the parallel motion at first, but then have a linear distribution going downward from the right to the left. So this right one here is wrong because that element doesn't have the linear distribution we expect due to the distributed load. This one looks just right. This one here is wrong because on the left element where there's no distributed load, they draw a linear distribution. So here's the right answer in the middle. Good. So the left answer here is wrong because we have no horizontal force in this system. So if we perform a cut on that vertical element, we should have no shear forces. Here they have shear forces in the vertical element. So this is wrong. Now, performing moment equilibrium at the left pin support, we figure out that the force at the roller support will be going downward. So from the right to the left, we should have a jump downward. This is the only answer. Here is a jump upward, so here's the answer. Good. We're interested in normal forces. And we can see that the right part of the system, the last third on the right, is neither under compression nor under tension. The middle one is under tension thanks to that horizontal distributed load, and the left one is under even more tension due to the two distributed load that are applied. So what we're gonna have is this system here. Tension and a little bit less, and then 0 on the right. The horizontal part is clearly under compression here, so negative value there completely. Now the question is, do we have any linear distribution here on the left? That's completely impossible. For that we need a distributed load with elements in the length direction of the beam. That's not even possible. So is this one here possible? Let's look at it. Moment equilibrium at the pin support leads to the value of 0 forces at the roller support. So no normal forces in that inclined element. Here's the answer on the right. Okay, what's gonna happen here? We need to have a quadratic distribution first. Here on the right, the curvature is wrong. Unless you have the other curvature. Here on in the middle, the curvature is just right. Here on the left, it's constant, but we expect to have a quadratic distribution. So the answer is here in the middle without any further ado. Okay, here we have like a truss, and the trick here is to consider the whole truss like a beam, and the whole beam here under a distributed load would lead to tensile stresses on the lower part. So the lower horizontal elements are under tension, the upper elements are under compression. On the tension here, upper elements under compression, and then what happens in the middle is normally we can just compute it, but here this is the right answer. The other one had some jumps, I mean some wrong values basically. um Looking at this, what's gonna happen, that horizontal element we have is gonna be under tension. How can we see that? For moment equilibrium, just looking at the row vertical and horizontal elements with a moment equilibrium at the top node, we're gonna figure out that this horizontal element needs to be under tension. What's happened with the vertical element? Nothing. This is actually a right answer there. Oh man, I need to explain it a little bit faster. We're gonna have linear change here and distribution of the normal forces here in the two inclined elements. The vertical and the horizontal elements, there are zero elements. So here's our right answer here. Here we have constant distribution, but it's wrong because we expect linear variation of those normal forces. Here the zero value there at the node is questionable. So here's our right answer. The two rods that are connected there and subjected to a single load are, I mean, they are rods, as I said already, so they can't have any moment. That's why this right answer here is wrong. The left answer here completely ignored the distributed loadings, so the right answer is here in the middle. The right rod can't have any shear forces. It's a rod, as I said already. Now, what about this one? The way that the distribution here was drawn is wrong. For each element, we're gonna have a negative shear force, then a linear distribution, so that it goes a linear variation, so it goes to the positive value, and then for the next element, negative value, linear distribution, linear variation, so it goes to the positive value, and this right answer here is correct. The way it was drawn in the left part is wrong. With some of the force in the vertical direction, we figure out that at the parallel motion we have an upward force leading to tensile stresses and as leading to tension, let's say, in the inclined element. Tension in the inclined element, this value here, this answer here says 0 normal forces in the inclined element. This one says compression in the inclined element. Here's the right answer with tension in that inclined element. This is like a symmetric system. We don't have any horizontal loads here, so that force is basically gonna go, half of it is gonna go in the left column, the other half of it's gonna go in the right columns, and those columns are gonna be under compression. And when we cut the beam, the horizontal beam, we feel like we have no horizontal forces, so no normal force in the horizontal beam. What we're gonna have is this then, compression in the two columns and nothing in the horizontal beam. Now, what about this one? We need to have the quadratic distribution on that horizontal beam. Yeah. The two other elements are rods. On the left, they are rods, so they can't have any moment. Yeah, no one did that mistake. So here's our answer. Yeah, basically. We couldn't have, the middle value was 1 because we had a jump at the node. They couldn't have a value of the moment at the node. It needs to be 0 there, at the range, I mean. The left part, the overhang here of the horizontal element is not under compression, so it needs to be 0. So this left answer here is wrong. So now we just need to think about those two here. What's gonna happen? Where are we gonna have more compressive force here in the middle? Definitely when we did moment equilibrium at the left pin support. Okay, I need to be faster. The left rod can't have any value, so the left answer is wrong. The right answer is all wrong. Huh? Okay, so we have it already. Here's the right answer. The correct answer on the right. On the left there we have a rod, an element with two hinges, no loading perpendicular to its axis. So that's why. Here's the answer. So what happens here? The change of the value here in the horizontal element is 1. It's going upward. It should be going downward. So the right answer there is 1. What about this one? This is plausible. What about this one? This is also plausible, but having a value of 0, when we look at that hinge, we certainly have such a jump. Going there to a 0 value is not that plausible. So here's our right answer here. The overhang is neither under compression nor under tension, so we can't have any normal forces there. That's why this answer here is wrong. Now looking at this one, what happens here? This one is also wrong because we have no horizontal forces in the overhang, and then here they say suddenly that after we pass the first column that we have tensile forces, but that column, that rod can apply any normal forces. So here's our answer. And with that, we've completed level 5. So thank you for listening. I realized that the explanations needs to be done a little bit faster. Then it's not easy, but you also have you have done all the levels this far, so you have more experience. So see you next time.